Okay, thank you for introducing me and thank you for having me. In this morning, last night in my time zone, Hikita presented his work on Stanley-Sandbridge conjecture. So in this talk, I will talk about the refinement of his work and the refinement, uh, the connection with the refinement and the Heisenberg variety. Okay, if you have any question or comment, you can inter uh, please feel free to ask and leave the message on the chat. Okay, let me start. So I will start with the basic definitions, but I hope all of you are familiar with these very basic things. So I will I I do not want to my time on this slide, so let's briefly check. The partition is the weakly decreasing sequence of positive integers, and we will use this Young diagram, which is the array of the unit cells. And semi-standard Young tableau and standard Young tableau is filling of this Young diagram with certain conditions, but I do not put it down on this slide, and there is such inequalities. So we denote T SYT of lambda is the set of the standard Young tableau of shape lambda. And okay, let's move on to next. So symmetric function is the form of power series, which is satisfying these conditions. And we denote lambda sub n, the space of symmetric functions of homogeneous degree n. And there are many well-studied bases of this space. And in this talk, we only consider the following two bases. The one is elementary symmetric functions. We write E sub lambda. And one is the sure functions, which is S sub lambda. But as before, I assume that you are familiar with this definition of two bases. And let's define the chromatic symmetric functions. So we have graph G with the vertex set V equals n. And the proper coloring of G is a function from V to the positive integer set, such that if you have an edge between the vertices U and V, then the coloring on these two sets should be different. And we denote C of G, the set of all proper colorings of G. Then Stanley defined the chromatic symmetric function of G as the formal power series of this generating function of the proper coloring with this monomial. Then by definition, this chromatic symmetric function is actually the symmetric function. And there is a integer sequence called Heisenberg function. So a Heisenberg function of length n is a weakly increasing function from n to the set n to n, and this set is 1, 2, n, with satisfying this inequality. So the sequence 2, 3, 5, 5, 5 is one of the Heisenberg function. And we denote H sub n, the set of Heisenberg function of length n. Then there is a few combinatorial object associated this sequence. Then this is the thick path. And the Hessenberg function 2, 3, 5, 5, 5 correspond to this thick path. The height of the right step is R2, 3, 5, 5, 5. And there is also a poset corresponding to this 2, 3, 5, 5, 5, which means there is unit cell under this thick path. Then this unit cell denote, yeah, we have red one. This is 1, 2, 2, 3, 3, 4, 4, 5, and this one is 3, 5. Then using this unit cell, you can define the poset, this poset, and also you can consider the incompatibility graph of this poset, and is this. So we will use the identification of this all combinatorial object, and we denote all of them by M. Then we can define chromatic quasisymmetric function on the graph G, which is the generating function of the proper coloring as the definition of chromatic symmetric function. But the only difference is this Q weight, Q to the ascent of the proper coloring. But in this talk, this definition of ascent is not important, so I will skip the definition. By definition, when Q equals 1, the chromatic quasisymmetric function is actually a chromatic symmetric functions. And in general, the chromatic quasisymmetric function is not a symmetric function. But if you take your graph as the Hessenberg function, the graph from the Hessenberg function, then the chromatic quasisymmetric function is symmetric function. Okay, and there is a famous conjecture in algebraic combinatorics called E-positive conjecture. The Stanley also called Stanley-Stembridge conjecture. Stanley and Stembridge conjectured that the chromatic symmetric function of Hessenberg function is E-positive, which means the coefficient of the E lambda is always non-negative integers. And Shersian and Wax, when Shersian and Wax defines the chromatic quasisymmetric function, they also conjecture that the quasisymmetric function of the Hessenberg function, the graph of Hessenberg from the Hessenberg function is also E positive. And this means the coefficient of E lambda is non-negative integer polynomials. Then as Hikita presented, he proved the Stanley-Stembridge conjecture using his new the rational function he introduced. So I will give a brief, let's brief his result. So take a standard Young tableau T. Hikita introduced a rational function on this T. We denote by P sub m of T such that the chromatic quasisymmetric function is given by this formula, which means the coefficient of E lambda we denote by C lambda of Q is given by this form. And then Hikita proved that Hikita provided a probabilistic interpretation of these rational functions. Then he showed that this rational functions is greater or equal to 0 when Q equals 1. Using this, Hikita proved that the Stanley-Sternberg conjecture is true. Let's see an examples. So let M equals 355,666, and let lambda equals 551 partition, and we have this Young diagram, and T1, T2, T3 be such standard Young tableau. Then you can find this expression using your computer or by hand, and the coefficient of E5 lambda, E sub lambda is equal to these polynomials. And also you can find this P of T1, P of T2, P of T3 are given by these rational functions. And here P bar of T is equal to the times of the denormalized rational functions. And you can find this term is equal to this term. Then we can observe we have some observation on these examples. So this P bar of T is not a polynomial in general, but as Hikita proved, the summation of P bar of T is a polynomial. In fact, this is the coefficient of E sub lambda. But let's see the first two tableaux. So if you can check P sub P of T1, P bar of T1 plus P bar of T2 is a polynomial. It is not very difficult. And you have these polynomials. Then what is the common feature does do these first two tableau shares, and what is the difference between first two tableau and the last one? The difference is the position of the largest entry, 6. In first two tableau, the largest entry, 6, lies on the last column in here. But in the T3, the largest entry, 6, lies on the first column. Furthermore, the polynomial P bar of T1 plus P bar of T2 is divided by 5Q. This is Q integer 1 plus Q plus Q to the 4. Then you can check that this polynomial is divided by the 5Q. Then using this observation, we can define this set. So SYT sub K of lambda is the set of standard Young tableau of shape lambda the largest center n is in the kth column of T. Then from the previous observation, we have this one is a polynomial. So using this, we can define the following new variant of chromatic quasisymmetric functions. So E sub mk is equal to k over 1 and the summation of summation over standard Young syt sub k of lambda, and this sum up of these values and put this one as the coefficient of E sub lambda. And also E sub lambda, E sub m is defined to be the sum of E sub lambda and k. And by definition, you can find these expressions. So the chromatic quasisymmetric function is given by the summation of k times E sub mk. So we have a decomposition of chromatic quasisymmetric function, and we call this one and this one are a variant of chromatic quasisymmetric functions. Okay, and let's move on to geometry. Also, I hope that you are familiar with this well-known fact. So I don't want to my time on defining the Hessenberg variety. So Hessenberg variety is a subvariety of flag variety, which have very interesting, many of interesting combinatorial interesting properties, and Brosnan-Chow and independently Gipake proved that the chromatic quasisymmetric function is equal to the Frobenius characteristic of cohomology of the Hessenberg variety corresponding to the M. So I hope you are familiar with this fact. And Abreu and Nigro goes the further. They applied the decomposition theorem of Valens, Bernstein, Deligny, and they have the following decomposition. The cohomology of Hessenberg variety can be decomposed into the smaller pieces like this, and they also decompose chromatic quasisymmetric function using these decompositions. So this is Frobenius characteristic and omega involution. Also, this is the Frobenius characteristic with omega involution. So they define a new symmetric function G sub mk, which is given by the Frobenius characteristic of these pieces. And as they positively conjecture, they also conjecture that their new symmetric function G is also E positive. Using this G function, we also define this two symmetric function, which is very, you can find this one and this one is equal. Then you have also, yeah, okay. So we can define large G sub mk and large G sub m, which is also a variant of chromatic quasisymmetric function. Okay, and let's see the Schur expansion of chromatic quasisymmetric functions. So there is a P tableau, which is the filling of Young diagram of shape lambda with the following condition. And we denote by T sub m of lambda the set of the P tableaus of shape lambda. Then Gasharov proved, Gasharov and Shershan-Wax proved that chromatic quasisymmetric functions is given by these Schur expansions. So if you want to compute the Schur coefficient of chromatic quasisymmetric functions, then you the P tableau gives the answer. Similarly, Abreu and Nigro give the following problems, which finding a combinatorial description of their G function, a coefficient of Schur expansion of their G functions. And as before, we want to define a variant of chromatic quasisymmetric function, so we define a new subset of P tableau denoted by T prime of M, which is the set of the P tableau of shape lambda, and their first entry is equal to 1, which means your tableau should have 1 on here. Then we define S sub m is equal to the sum of Schur functions over this new subset of P tableaus. Okay. Then as summaries, we have defined the following variant of chromatic quasisymmetric functions. The first one from Hikita's work. The second one from Abreu Nigro's result. And the last one from Schur expansion. Then our main result is the following. So if you have a simple function m, then these three variants of symmetric functions coincide. And furthermore, E sub mk is equal to G sub mk. Then this main theorem gives the following corollaries. So if this one we saw at the beginning of this talk is actually a polynomial. And we also have the answer of Abreu-Nigro's conjecture when q equals 1. So there's new G function is a positive. Let's see. Okay, this E M K X Q is by definition KQ, and T is in SYT sub K lambda, and P bar T E lambda is equal to G sub MK, which is given by E k ek g m sub n minus k xq. Then when q equals 1, we have the e-positivity of this one, because this coefficient is always this coefficient is always be positive. So we have the answer of Abreu-Nigro's conjecture when q equals 1. And also we have the partial answers to Abreu-Nigro's questions. So we have the following sure expansion of this function. This is g sub m, and this is s sub m. Okay. So idea of the proof is the following. Gipake introduced a modular role to study chromatic symmetric functions, and Abreu and Nigro refined the modular role to characterize the chromatic quasisymmetric functions. So if you have a function f from Heisenberg function to Q algebra satisfies the modular role if q 1 plus q times f m prime is equal to q times f of m plus f2 prime of m, when m prime m2 prime is a modular threefold of type 1 or type 2. Then Abreu and Nigro proved that the function satisfies the modular role is uniquely determined its values on the disjoint union of complete graphs. And this is the definition of modular threefold. So you have two yellow box here on the above this path, then
okay, thank you very much. Let's thank Byung-Hak again. And so now we have the last coffee break of the of today. We'll have one more talk after this, and so please stick around. For now, I put together the submissions to the 2 icebreaker forums. So we're going to go through those real quick. I'm going to share a screen. And they are very, very funny and very exciting to share. So I'm going to share a screen here. Okay, so first let's do the icebreaker. So in the morning, those of you who are here in the morning, we had to choose the correct answer between algebraic combinatorics, which 76.7% of this audience chose, and which makes sense because we're alcove. Then geometric combinatorics got, does it say, 6.7% of the votes. Topological combinatorics, enumerative combinatorics, enumerative geometric topological algebraic statistics got 1 vote. Analytic combinatorics got 1 vote, and algebraic and geometric combinatorics got 1 vote, which I think was probably an other submission that somebody just typed in. So this was the distribution. Which of the following are sandwiches? We had 7 votes for taco, 5 for burrito. Most people thought quesadillas and avocado on toast were sandwiches, but lower votes for ravioli and fried chicken and things like that. The worst tableau was, I wish it showed the pictures. It was just something that was a kind of a funny thing, I think, with the walls. It was like a walled tableau. And nobody really thought the highest vote tableau was very bad, but there was 1 vote for that, and the others were pretty well distributed. I found it interesting that most people thought W comes after X, Y, and Z. When you run out of letters, you use W. I could tell that we don't have any physicists in this conference because we don't have any T, so nobody voted for, like, 3 dimensions and then time for space-time. But some people use A or S, it turns out, and alpha is a good one as well. And which of these are most cursed? The fraction with chi bar over chi, I think, or c bar over c, written in uppercase Greek letters, and let epsilon be less than 0. Somebody submitted another one saying, we are excited to welcome you to Alcove 2025 from Lorenzo's email, because we're not allowed to use exclamation points after a number unless we mean factorial. So that's also really good creative submissions. So there's also some things in the chat I'm not keeping up. Sandwich is anything you can apply the ham sandwich theorem to. I think that's a good thing. And there's also a Norwegian letter past Z. That's a really good idea. All right, so that was the icebreaker responses. And now I want to talk about the discrete objects photo contest, which our judging panel reviewed them very carefully. That was me. It was the entire judging panel. And so I just picked out some ones that I thought were really notable, and I gave them like a prize, but all of them were very notable. So everybody who submitted gets to see their picture on this document. So I just copied over the pictures in no particular order, except the winner is at the bottom. And the winner is, you'll see it's very clear who the winner is. So the number of thread lines in one cross section I thought was an interesting discrete object. And my question on this one is it really discrete, right? Because it sort of wraps around in the back, but I don't know, maybe you're just sort of looking at the photo itself. So maybe 175, I don't know. Okay, so that was submitted by Alexander Diaz. Yannick Yao submitted a picture of a screen, I think, like a window screen, and all the holes in the window screen. Yeah, maybe 10 to the 5th. That was a good submission. We have a couple of people submitted pictures of leaves on trees. So it was a nice day at CSU. So I took a photo at our watch party and estimated 100,000 leaves. I have no idea if that's a correct estimate. There was a lot of good pictures of chalk and markers and things like this. So 175 pieces of chalk estimated here by Mary Claire Simone. We had a submission of 6 items by Mike Joseph with an interesting formula that I'm assuming comes out to 6. And so I awarded this most interesting formula for submission. So that's also just a very visually appealing picture. There were coffee grounds, maybe 1,000. I don't know if it's coffee grounds. I'm not sure what this picture is by Laura Pearson.
Yeah, they're coffee grounds.
Yeah, definitely speak up if you want to like say in the chat or just unmute to tell me what these things are. Okay, coffee grounds. Awesome. I awarded this one most visually beautiful image because I thought the sort of going down the hallway with all the stones was just very nicely arranged in this photo. And Harper estimated 101,000, so probably so that the picture would beat any submissions that estimated 100,000. And so I thought this was a very nice image of stones. We had 2 very tasty looking submissions by Olya Mandelstam, or maybe the whole Waterloo team. I wasn't sure. There was a picture of I think onion rings. If Olya is here, you can tell me. And the cupcake has 13 sprinkles on it. So I awarded this most tasty. And then these are barley couscous grains in a jar, which I think is a very good jar of things, like a jelly bean contest, with an unsure number of them, but submitted by Amy Myers. 2,000 books submitted by Guilherme Zeus Dantasemora in a library. 350 little, I think, crystals on this crystal tree by Jake Levinson, and I awarded this most purple. And then we had 100, maybe 10,000 coffee beans in a jar by Andy Wilson. More trees. We have Ryota Inagaki saying at least order 10 to the 4th leaves. This was definitely awarded. The smallest number submitted was 2 markers by Kyle Soloy. And then we had another picture of trees, maybe 400,000 leaves by Andrew Reimerberg. 980 blueberries by Elsa Frankel. And finally, the winner was somebody who just submitted a screenshot and said 2,304,000 pixels by Leigh Foster. So that was the winner. That was very creative because you can actually just look up how many pixels are on your screen. And so, and yes, they are discrete objects. So that actually won the contest in terms of how many different discrete objects people could find. So congratulations to everybody who submitted an image, and I hope everybody had fun. All right.